This is a recast of the 6,100-word piece, Adaline, Adaptive Linear and NEuron, from Snippet AI. This article discusses the concept of Adaline, also known as Adaptive Linear and NEuron, and its significance in artificial neural networks. Adaline is a single-layer artificial neural network that adapts and learns from input data, making it useful for pattern recognition and classification tasks. It was developed as an improvement to the original perceptron algorithm and incorporates advanced mathematical principles. The article explores Adaline's structure, functioning, strengths, limitations, and practical applications, as well as its impact on the field of artificial intelligence. It compares Adaline to other neural network models and discusses its future trends and areas for research. Let's listen in.
In this article, we're going to explore the concept of Adaline, also known as Adaptive Linear and NEuron, and its significance in the field of artificial neural networks. Adaline is a single-layer artificial neural network that was developed as an extension of the perceptron model. It incorporates advanced mathematical principles to adapt and learn from input data, making it a powerful tool for pattern recognition and classification tasks.
That's right. Adaline was developed in the 1960s by Bernard Widrow and Ted Hoff as an improvement to the original perceptron algorithm. The perceptron had limitations in handling continuous input patterns and dealing with linearly non-separable data. Adaline's architecture consists of a single layer of nodes, where each node computes a linear combination of its inputs using adjustable weights.
And one of the interesting features of Adaline is its ability to utilize a bias term. The bias term acts as an additional input that is always equal to 1, and it is multiplied by a separate weight. This allows Adaline to learn and adjust its decision boundary not only based on the data points themselves, but also based on a constant term. This can be particularly helpful in situations where the data does not naturally separate in a linear manner.
Exactly. By including a bias term, Adaline becomes more flexible and versatile in capturing complex patterns, making it a powerful tool in machine learning applications. It can adapt and learn from input data, making it useful in various domains such as pattern recognition and control systems.
The purpose of this essay is to provide an in-depth understanding of Adaline by detailing its structure, functioning, and practical applications. It aims to examine its strengths and limitations, comparing it to other artificial neural network models. By studying Adaline's historical context and its impact on the field of artificial intelligence, we can appreciate its contributions and consider its relevance in contemporary machine learning systems.
Adaline has had a significant impact on the field of artificial intelligence. Its development can be traced back to the late 1950s when it was introduced as a precursor to the perceptron. Bernard Widrow and Ted Hoff played a crucial role in its development at the Stanford Research Institute. Adaline incorporated the concept of linear regression to adapt its weights based on input data, allowing it to learn and make predictions by minimizing the error between its output and the desired output.
This breakthrough approach laid the foundation for more complex neural network architectures. Adaline's success marked a significant advancement in the field of artificial intelligence and paved the way for future innovative developments.
Adaline's origins can be traced back to a research project conducted by Bernard Widrow and Martian Hoff at Stanford University in the late 1950s. They aimed to create a system that could adapt to and learn from its environment. Inspired by Frank Rosenblatt's perceptron, Widrow and Hoff sought to enhance its capabilities by introducing adaptive features. This led to the development of Adaline, an artificial neural network model that employed linear activation and adjustable weights to learn and make predictions.
And it's important to note that Adaline has proven to be useful in various applications beyond its initial development. It has been used in pattern recognition and control systems, and it has laid the foundation for more advanced neural network architectures that we see today.
Absolutely. Adaline's ability to adapt and learn from input data makes it a powerful tool for pattern recognition and classification tasks. Its utilization of advanced mathematical principles allows it to handle continuous input patterns and linearly non-separable data.
Right. And one of the key advancements in the Adaline model is the introduction of the backpropagation algorithm. This algorithm, proposed by Geoffrey Hinton in 1986, allows the model to learn from its mistakes by adjusting the weights in the network. By comparing predicted outputs with desired outputs and updating the weights based on the error, the model becomes more accurate over time.
Backpropagation has revolutionized the field of artificial neural networks. It has made Adaline a powerful tool in machine learning applications. The ability to learn from mistakes and update weights accordingly has greatly improved the model's performance and accuracy.
Definitely. And it's worth mentioning that Adaline's effectiveness lies in its ability to handle linearly inseparable data. It does this by employing the Widrow-Hoff learning rule, which updates the weight values incrementally. This allows Adaline to handle complex classification tasks that other models may struggle with.
Adaline also overcomes the limitations of the perceptron algorithm by utilizing a continuous activation function. This means that Adaline can compute real-valued outputs, providing more flexibility in capturing subtle distinctions between patterns. This is particularly useful in applications like handwritten digit recognition, where Adaline can accurately analyze and classify different numerical characters.
Absolutely. The perceptron model, which serves as the foundation for further developments in artificial neural networks, is quite different from Adaline. While both models belong to the class of linear threshold units, there are some significant differences between them.
That's right. One major difference is that Adaline has a weight adjustment mechanism that allows for continuous adaptation, while the perceptron adjusts its weights based on a binary learning rule. This means that Adaline has a greater learning capacity and can handle more complex tasks compared to the perceptron.
Another difference is the activation function used. Adaline employs a linear activation function, which allows for a more diverse range of input-output mappings. On the other hand, the perceptron uses a step function producing binary outputs. This means that Adaline is better suited for tasks that require more nuanced outputs.
Overall, Adaline and the perceptron have their own strengths and weaknesses. Adaline's ability to continuously adapt and handle complex classification tasks sets it apart from the perceptron. However, the perceptron still has its uses and has laid the foundation for further advancements in artificial neural networks.
That's right. It's important to understand these differences and strengths when considering which model to use for specific tasks in machine learning and pattern recognition.
Absolutely. Adaline's development and evolution, along with its collaboration between Dr. Bernard Widrow and Marcian Hoff, have paved the way for more advanced neural network models that we see today.
And that wraps up our discussion on the main points of the article. We hope you found it informative and helpful in understanding the contributions of Dr. Bernard Widrow and Marcian Hoff to the development of the Adaline model, as well as the evolution and improvements over time.
Thanks for listening to our podcast. Stay tuned for the next episode where we'll dive into another interesting topic in the world of technology and artificial intelligence.
Until then, remember to stay curious and keep learning. In our previous episode, we discussed the Adaline algorithm and its potential applications in various fields. Today, we're going to explore the limitations and challenges faced when implementing Adaline, as well as how it compares to other machine learning algorithms.
That's right, Ben. While Adaline has its advantages, it also has limitations that need to be considered. One major limitation is its reliance on linear activation functions. This means that it struggles to handle complex patterns and non-linear relationships. So when it comes to classifying datasets with intricate decision boundaries, Adaline may not be as accurate as desired.
Absolutely, Avery. Another limitation is that Adaline's performance heavily relies on the quality and quantity of training data available. If the datasets used for training are inadequate or biased, it can lead to inaccurate predictions and compromise generalization capabilities. So having a diverse and representative dataset is essential for obtaining reliable results with Adaline.
And let's not forget about the computational intensity of Adaline's training process. Dealing with high-dimensional feature spaces or large datasets can make the training process time-consuming and resource-demanding. This is something that needs to be taken into consideration when implementing Adaline in real-world scenarios.
Absolutely, Avery. Overcoming these limitations and challenges is an ongoing area of research to enhance the performance and applicability of Adaline. Now let's talk about how Adaline compares to other machine learning algorithms. One advantage of Adaline is that it employs a continuous linear activation function, unlike the perceptron algorithm which uses binary outputs. This allows Adaline to learn even when the output is not binary.
That's right, Ben. Another advantage of Adaline is its ability to optimize its weights iteratively using the gradient descent algorithm. This enhances its learning capabilities and allows it to adapt to different datasets and patterns.
And one of the strengths of Adaline is its ability to handle numeric input features without the need for additional preprocessing. This proves to be advantageous in numerous applications where preprocessing can be time-consuming and complex.
However, it's important to note that Adaline's convergence is highly dependent on the input data and the feature scaling technique employed. So, understanding the characteristics of the dataset and choosing the appropriate feature scaling technique is crucial for the success of Adaline.
Moving on, let's discuss some case studies that further highlight the effectiveness and practicality of Adaline in real-world applications. One such case study involved the classification of handwritten digits from the MNIST dataset. The Adaline algorithm demonstrated impressive performance with an accuracy rate over 90%.
That's right, Ben. Another case study focused on the prediction of stock prices using historical market data. Adaline was able to successfully predict the direction of stock prices with a high level of accuracy. This makes Adaline a promising tool for financial forecasting tasks.
These case studies emphasize the versatility and practicality of Adaline in various domains. For example, in the field of medical diagnosis, Adaline has shown its potential as a valuable tool. By analyzing patient information such as symptoms, lab results, and medical histories, Adaline can provide predictions on the likelihood of different diseases, assisting doctors in making more informed decisions.
Absolutely, Ben. The ability of Adaline to adapt and learn from new information ensures that it can continuously improve its diagnostic accuracy over time. This can significantly benefit the medical community by potentially reducing misdiagnoses and leading to better patient outcomes.
And that wraps up our discussion on the limitations, challenges, and applications of the Adaline algorithm. It's clear that while Adaline has its strengths and limitations, it has proven to be a valuable tool in various fields.
Thanks for joining us today, and remember to stay curious and keep learning. See you next time.
Welcome back to our podcast. In today's episode, we're going to dive into an interesting article we came across about the Adaline algorithm and its applications in various fields.
That's right, Ben. The article highlights how Adaline has been successfully utilized in autonomous vehicle navigation, enhancing the capabilities of self-driving cars. By utilizing Adaline's adaptive learning mechanism, these vehicles are able to continuously update their route planning and decision-making processes based on real-time data and feedback from sensors.
That's fascinating, Avery. The integration of Adaline in autonomous vehicles allows them to adapt to changing traffic conditions, avoid obstacles, and make informed decisions about acceleration, braking, and lane changing. This significantly improves the overall safety, efficiency, and reliability of autonomous vehicle navigation systems.
Absolutely, Ben. Adaline, which stands for Adaptive Line and NEuron, is a variant of the perceptron algorithm proposed by Bernard Widrow and Ted Hoff in 1960. Unlike the perceptron, Adaline utilizes a continuous activation function, which allows it to make gradual adjustments to its weights and biases.
That's a great point, Avery. The continuous nature of Adaline enables it to converge to a solution even when the input data is linearly separable, unlike the perceptron, which may struggle with such cases. Additionally, Adaline incorporates a learning rule known as the Widrow-Hoff rule, which utilizes the stochastic gradient descent algorithm to optimize its weight values.
Right, Ben. These features make Adaline a valuable tool in applications such as pattern recognition and signal processing. Its ability to continuously learn and adapt based on input data makes it highly versatile and efficient in solving classification tasks.
Definitely, Avery. The article also points out some future trends and areas for further research. For instance, investigating the integration of Adaline with other advanced algorithms like deep learning architectures could potentially yield more accurate predictions.
That's an interesting point, Ben. Deep learning has been a hot topic in recent years, and combining it with Adaline could lead to further advancements in the field of machine learning.
Absolutely, Avery. The article also suggests exploring the impact of different learning rates and activation functions on Adaline's performance. This could potentially lead to significant improvements in its capabilities.
Another area for future research mentioned in the article is the potential applications of Adaline in real-time systems, such as robotics and autonomous vehicles. Investigating its usability and optimizing its performance in these industries could open up new possibilities.
That's a great point, Avery. Adaline has already shown great potential in autonomous vehicle navigation, but there is still much to explore in terms of its application in other real-time systems.
Absolutely, Ben. The article concludes by discussing some potential challenges and areas of improvement for the Adaline algorithm. For example, its reliance on a linear activation function limits its ability to handle nonlinear problems effectively.
That's a valid concern, Avery. Incorporating a nonlinear activation function could enhance Adaline's learning capability and allow it to tackle more complex datasets.
Exactly, Ben. Adaline's sensitivity to the initial weights and bias values is another challenge that needs to be addressed. Efficient techniques to initialize these parameters can help improve the algorithm's performance.
Right, Avery. The article also mentions that Adaline might suffer from high computational complexity when dealing with large-scale or high-dimensional datasets. Developing strategies to mitigate this challenge is crucial for improving scalability and efficiency.
Absolutely, Ben. Despite these challenges, the Adaline algorithm has made significant contributions to the field of artificial neural networks. Its unique architecture and learning capabilities have revolutionized pattern recognition, data classification, and signal processing.
Definitely, Avery. Adaline's adaptability and ability to continuously learn from input data make it a powerful tool in various domains. Its potential applications in artificial intelligence, speech and image recognition, and even robotics are truly exciting.
That's right, Ben. Adaline's future prospects are promising, but further research is needed to fully explore its capabilities and optimize its performance in complex datasets. Nonetheless, it's clear that Adaline has already made significant advancements in the field of machine learning.
Absolutely, Avery. Understanding the functionalities and implications of Adaline can greatly contribute to the advancement of machine learning techniques and artificial intelligence research. It's an exciting time for this adaptive linear neuron model.
And that wraps up our discussion on the main points of the article. It's clear that Adaline has shown great potential in various fields and will continue to be a valuable tool in advancing machine learning and artificial intelligence.
Thanks for joining us today, and remember to stay curious and keep learning. See you next time.